Welcome back to Physics 141 Online. We've already talked about several special kinds of thermodynamic processes and what's happening in those processes. For example, we talked about isothermal processes, and we talked about constant pressure or isobaric processes, and then isovolumetric processes. And the last of the special processes is a little bit more complicated than the others. It's called an adiabatic process. And an adiabatic process occurs when there's no thermal energy or heat exchanged between a system and its environment. And this can happen really in two ways in a practical sense. Either the system can be very well insulated from its environment, maybe through the use of insulating material that makes it very difficult for heat to get in or out, or we can have a process that happens so rapidly there's no time for any significant amount of heat to be absorbed or released. Either way, such a process is called adiabatic. And during an adiabatic process, both the pressure and the volume change, but they change in a different way than they do for an isothermal process. And so we want to do some calculations to figure out how it is that the pressure and the volume change. So practically, we would like to know if we know the initial pressure and the initial volume, and then there's an adiabatic expansion or compression, how can we find the final pressure and the final volume? And there's a very simple relationship that we can derive. It takes a little bit of work, but we can get it, and that will help us understand how the pressure and the volume vary. So first, let's consider an adiabatic expansion. Expansion meaning the volume goes up, and let's think qualitatively about what happens so that we can draw a PV diagram to illustrate the adiabatic expansion. So, what happens first? V increases. And if V increases, that means the work done on the gas is less than zero. The work is negative. The gas is pushing out, and so that means the work done on the gas is negative. Now, it's adiabatic, so just by definition, we know that Q is equal to zero. So now what are the consequences for the first law? Well, the first law says delta U is Q plus W. Q is zero, so delta U is equal to W. W is less than zero, so delta U is less than zero. And we can then draw one more conclusion about the temperature, because delta U is proportional to delta T. So if delta U goes down, that must be because the temperature goes down. And we have deduced very simply that in an adiabatic expansion, the temperature decreases. And by contrast, if it were an adiabatic compression, the temperature would go up. This helps us to draw what happens on a PV diagram. So this means the gas expands from P1V1 to P2V2, and in the process it goes to a lower temperature. The kind of curve that we want to draw is called an adiabat, which tells us what all the intermediate pressures and volumes are when a process undergoes this kind of an adiabatic expansion. Now, the two dotted lines are isotherms. Those are curves that would show how the pressure and the volume change at constant temperatures. So imagine that we're starting at P1 and V1 and at a higher temperature T1, which is up here. We know that as we go to P2, V2, it has to pass to a lower temperature. And here we have a second isotherm at a temperature T2, which is lower than T1. And I know it's lower than T1 because all the points on that curve are closer to the pressure and the volume axes than the points on the T1 isotherm. So this shows that we're going from a higher to a lower temperature in the expansion process. And to analyze, to get a relationship for how P depends on V, it's not really just obvious looking at the curve, but what we can do is consider a very small step, an infinitesimal step along the path. And for that step, we'll say that the internal energy changes by an amount dU, and that's equal to a heat transfer dQ and a tiny amount of work dW. But for an adiabatic process, Q never changes, so dQ is zero. That means du is dW, and from our previous discussion, when we talked about pressure, volume, work, we know that dW is minus pdV. The minus sign is there because if the volume goes up, that means negative work is being done on the gas. So what does this do for us? Now for a monatomic gas, we know the expression for U. We know that U is 3/2 nRT, so du, the change in the internal energy, is 3/2 nR dt. So that's the left-hand side of this equation. The right-hand side is negative PdV. So we've got a relationship that says for anything that happens along this curve at a particular pressure P, the temperature change and the volume change are related to this equation here. So what we do now is use the ideal gas law, and we're going to take PV equals nRT and take the differential of both sides of this equation. And we use something like the chain rule. When P and V are both changing, then taking the differential is P times dV plus V times dP, right? And that then is equal on the right-hand side to nR dt, because n and r are constants. So this product PV, when we take the differential of it, it gives us two terms. And you're familiar with something like this from your calculus course. Now, what we now do is take the equation from the previous slide, du, which is 3/2 nR dt, that's equal to minus pdv, and compare it to this equation up here. And what we notice is that this nR dt term appears in both equations. So we're going to replace nR dt in the bottom equation with the sum of the two terms in the top equation. So this becomes 3/2 pdv plus vdp is minus pdv. Now we just need to do a little bit of rearrangement. So we've got 3/2 pdv, and then we've got a negative pdv. And when we collect those two terms and then relate them to the VDP term on the other side, we get PDV is minus 3/5 VDP. And let me just pause for a second to remind you what this means. This now is getting to be very close to the final answer, because it's telling us how the volume change and the pressure change are related to each other along the curve that represents an adiabatic process. So we would like to take this equation and use it to solve for P in terms of V. And it's just a few steps with calculus to do this. The technique that we use involves what's called separation of variables. We got two variables in this equation, V and P. So we'd like to get all the terms that relate to one variable on one side of the equation and all the terms that relate to the other variable on the other side of the equation. And when we do that, we just divide both sides by P and divide both sides by V and do a little bit of separation. We find that dP over P is equal to minus 5/3 dV over V. All right, so these two fractions now are things that we can integrate. We can add up the changes in those quantities as we move along the curve from some initial pressure P1 to a final pressure P2. Of course, as we do that, we're also going from an initial volume V1 to a final volume V2. So we can integrate. If those two sides of the equation are equal, we can also add them up, and we can integrate along that path and add up these quantities. Because as long as we're starting and ending at the same point on the PV diagram, then these two sides are still equal. So what that does, you'll recognize from integral calculus that the integral of dP over P is the natural log of P. And the natural log of P then, with the upper and lower limits, that would give on the left-hand side log of P2 minus log of P1. And a nice way to write that compactly is log of P2 over P1. All right, so then we do the same thing on the right-hand side of the equation. The only difference is there's a minus 5/3. So it's minus 5/3 log of V2 over V1. And one nice property of natural logarithms is if you have the log of a quantity and then a number out front multiplying that log, that's the same as having that number as the exponent of the natural logarithm. So this minus 5/3 log of V2 over V1 is the same as the log of the quantity V2 over V1 to the minus 5/3 power. And finally, one last rearrangement. It's kind of a little bit awkward to have this negative exponent, so something raised to a negative power is the same as the reciprocal raised to the positive power. Right? So V2 over V1 to the negative 5/3 is the same as V1 over V2 to the 5/3. So now we've actually got a pretty nice relationship. We can relate the natural log of this ratio of pressures to the natural log of this ratio of volumes, V1 and V2. And what do we do with this? When we have two quantities involving natural logs, we take E and raise it to the power of both sides. And that preserves the equality between these two quantities. And in fact, what we get is P2 over P1 has to be equal to V1 over V2 to the 5/3. Right? If the natural logs of these two quantities are the same, then the two quantities themselves have to be the same. So we're almost finished. We're almost finished. Now we can see that this, through cross multiplication and rearrangement, can be written in this final form, that P2 times V2 to the 5/3 is equal to P1 times V1 to the 5/3. And remember, this is just for a monatomic ideal gas. We assumed the ideal gas law, and we assumed the equation for the internal energy of a monatomic gas like helium or neon. In general, instead of writing it with the 5/3, we'll write it in the most general case with a power that we'll call gamma. And we've seen this gamma before in the equation for the specific heat of gases. And just to remind you, for a monatomic system, like helium again, gamma must be 5/3. That's the result that we got above. For a diatomic system, gamma is 7/5 or 1.4. And there are other kinds of more complicated systems where the gamma value could be something even slightly different from these two. But these are the two most common cases that we will encounter in this part of the course. So, just to summarize then, what we've done is, just from very first principles, from the first law of thermodynamics, from the ideal gas law, and the use of a little bit of calculus, we have found that there is this relationship for how the pressure and the volume change in an adiabatic process. This equation only holds true for an adiabatic process. It does not invalidate the ideal gas law. It's still true that PV is equal to nRT, but this imposes an additional relationship between the pressure and the volume as we move along an adiabatic curve, indicating the change from some initial to some final state of a gas. So, the adiabatic expansion or adiabatic compression is such that the pressure and the volume changes are always related by this general equation. So, we've now finished our consideration of special thermodynamic processes, and we'd like to begin looking at processes that involve more than one of these. And the example that we'll look at in class involves a two-step process that has first an isobaric expansion and then an adiabatic expansion. And we'll use this to give us practice for calculating thermodynamic quantities like the internal energy change, the work done on the gas, the heat absorbed by the gas, and so on. I'll see you in class.